this section, we're going to be looking at the area of a region between two curves. So we're going to go back to the idea from Cal 1 and just kind of review finding the area under a curve. So if I wanted to find the area bounded by the x-axis, the lines x equals 1 and x equals 4, and the graph of the function f of x equals 1/3 x squared plus 2. If you remember, this is going to be this graph is going to be a parabola. So if you were to sketch it out, it would look something like this. So your graph would look roughly something like this. And then we're looking at the region between x equals 1 and x equals 4. So if I were to draw some lines at x equals 1, 2, 3, 4, like so, about here, then you could see that you're roughly looking at the area of this shaded region. Get my graph a little bit more correct here. It's a sketch, it's not exact, but you get the idea. So the area, of course, is going to be the integral from a to b of f of x with respect to x. So that would be the integral from 1 to 4 of 1/3 x squared plus 2 with respect to x. So I would integrate, and I'd have 1/3 times x cubed over 3 plus 2 times x, and that's all going to go from 1 to 4, or x cubed over 9 plus 2x from 1 to 4. We'll plug in the 4 and have 4 cubed over 9 plus 2 times 4, and we'll subtract and have 1 cubed over 9 plus 2 times 1. Remember, this is that fundamental theorem of calculus. So that gives me, for the first part, 64 over 9 plus 8 minus 1 over 9 plus 2, which ends up giving me 63 over 9 plus 6. I'm just subtracting the 64 over 9 and the 1 over 9 and the 8 and the 2. And 63 over 9 is 7. So I get 13 units squared. And that is my answer for the area. So something that was implied in this process that you may not have realized is that we're actually finding the area between two curves. We're finding the area between the x-axis y equals 0 and y equals that 1/3 x squared plus 2. So we've been doing this process all along, we just didn't realize it. We're going to generalize it now. If you want to find the area between two curves G and F, whichever one is on top, in this case it's G, you can think of it as finding the area beneath G and the area beneath F and then subtracting the two. So the representative rectangles that we draw for the height of that shape at any point would be the height at g of x minus the height at f of x, or whichever order it's in. In this case, they've swapped the order. And the blue rectangle, of course, is shown as called a representative rectangle, and its width is delta x. Its height is the difference between g and x. So if we want to find the area of that individual rectangle, we would multiply the height and the width together. And if you add n of those rectangles together, you have the sum from I equals 1 to n of f of x of I minus g of x of I times delta x. So in order to actually estimate the area of the shape between those two curves, we want to take the limit as n approaches infinity and imagine that we have infinitely many rectangles. Which is going to be the integral from a to b of f of x minus g of x with respect to x. Actually going to define the area of the region between two curves. It'll be the integral from a to b, where those are the bounds, the left and right bounds, of f of x minus g of x divided by d of x, assuming that the f of x is greater than or equal to the g of x curve. And it's not necessary that both graphs actually be above the x-axis. So one of them could be above and one of them could be below. So if you had a situation like this where one curve is up here and one curve is down here, it will still work to find the difference between them by subtracting, because all of the negative points down here will just end up being added instead of subtracted, which gives you the area between the two curves. So it works regardless. Okay, so next we're going to work an example. It says find the area of the region bounded by the graphs of f of x equals x squared plus 1, f of x equals x, and the lines x equals 1 and x equals 3. So I'm going to start by sketching out a graph. I'm going to sketch out f of x equals x squared plus 1. So whichever method you're comfortable doing that is fine. I like to think of it as shifting the graph of x squared up 1 unit. So it looks approximately like this. It's a little bit out of the scope of our graph, but that's okay. We can still sketch it at least. So that is f of x equals x squared plus 1. And then f of x equals x is the line y equals x. So it looks like this. And we're looking between x equals 1 and x equals 3. So I'm going to drop some vertical lines there. And the area between those two curves and between those two lines looks like this. So again, not something that you would want to not something that you would want to calculate by a geometry formula. We're going to use the calculus here. So my area will be the integral from 1 to 3, because those are my bounds, of f of x, which is the higher curve, x squared plus 1, minus g of x, which is the lower curve, all with respect to x. And this is a really easy integral to calculate. It's just going to use the power rule, so we'll have x cubed over 3 plus x minus x squared over 2, and that's all going to go from x equals 1 to x equals 3. So I'll have 3 cubed over 3 plus 3 minus 3 squared over 2. And then I'm going to subtract 1 cubed over 3 plus 1 minus 1 squared over 2. 9 cubed over 3 is, 3 cubed over 3 is 9, plus 3 minus 9 halves. And here we get 1/3 plus 1 minus 1/2. And here we're going to have, let's see, 9 plus 3 minus 9 halves. We'll distribute the negative. And when we add all of this together, we get 20/3 units squared. This is still area. Okay, with this one, we're finding the area of the region bounded by the graph of f of x equals x squared minus 1, f of x equals x squared plus 1, and the lines x equals 2 and x equals 4. So again, I'm thinking of these two functions as the graph of x squared shifted either up or down. So when I graph these two functions and find the area, or the section between x equals 2 and x equals 4, you can see we're looking for the area of this long, skinny blue region right here. So the process is the same. The only thing that I'm really interested in is which function is on top and which function is on bottom, because that will change things a little bit. If you get it wrong, if you get those in the wrong order, you should end up with a negative number, and that would give you a big clue that, hey, I got this in the wrong order. So I'm going to have first x squared plus 1, and then I'm going to subtract x squared minus 1. And I notice that if I distribute the negative here, the x squareds end up going away. So I'm really taking the integral from 2 to 4 of 2 with respect to x, which is 2x. So we'll have 2 times 4 minus 2 times 2, which gives me 8 minus 4, or 4 units squared.